Today we're going to be talking about the second derivative test in concavity. So when we're looking at concavity of a function, y prime, so the derivative is decreasing, which means y double prime is less than 0, tells me our graph is concave down, or the slopes of the tangent lines are decreasing. Y prime is increasing, or y double prime is greater than 0, we're concave up. Or the slopes of the tangent lines are increasing. So concavity. A graph is concave up if y prime is decreasing. Increasing. Y double prime is greater than 0. We're concave down if y double prime is less than 0. Oh, that's what I have down here. Well, isn't that convenient? So really you just have to have the top written down. Okay? Remember that concavity happens on an interval. Keep that in mind. It's happening, your concavity of your graph is happening on an interval. Now, a point of inflection, this is really important, is where the concavity changes. So y double prime changes from positive to negative, or from negative to positive. And what you have to look at is you look at when y double prime equals 0, or when y double prime is undefined. Those are kind of your critical points for your second derivative. Okay, so I need to look for my concave up, concave down, and points of inflection. Now remember points, we're going to want an x, and we're going to want a y. Okay, so my recommendation on this is distribute that 1/3 through to both terms. When you distribute that through, remember you're adding the exponents. Okay, that makes your derivative slightly easier to find. Alright, x third, subtract 1, we get 1/3 plus 4/3 x to the negative 2/3. I know that we've told you guys not to have negative exponents. It's okay now. We're very strict in early classes, and we're a little less strict when we get to calculus. Find your second derivative. So we have 4/9 x to the negative 2/3 plus, we're going to need a minus in there because I bring down my exponent, negative 8/9 x to the negative 5/3. Now this is when you want to put those exponents in your denominator. And I'm going to leave them as fractions. Now we want these exponents to be the same. So I'm going to multiply this first term by x to the 3/3, which is really about like saying 1, over x to the 3/3. So that now our second derivative has a common denominator of 9x to the 5/3 over, that is on the denominator. 4x minus 8 is in the numerator. So now I set this equal to 0, so really I just need to worry about the top, and that gets me 2. Now you have to look at where your second derivative is undefined, and it's undefined, let me write a little notation, and x equals 0, because that's the number that makes our denominator equal to 0. So just like with our first derivative, we're going to make a little chart, but again, I might label it what this actually is. Sign of your second derivative. Put your values on there. So now you're looking at your second derivative. So plug in, again, numbers along the interval into this second derivative. If I plug in a negative, my denominator is negative. If I plug in a -1, my numerator is also going to be negative, so I have a negative over a negative, which is a positive number. Now I plug in 1. Any positive number, my denominator is going to be positive. If I plug in 1 in the numerator, we're going to get a negative. So we are negative on the interval from 0 to 2. And then at 2, if I plug in 3, we have a positive over a positive, so we are positive. So we are concave up. Let me erase so that it looks like words. Up on our interval from -infinity to 0 and from 2 to infinity. I chose to do interval notation. You don't have to. You can use inequality signs because f double prime of x is greater than 0. And again, justification using writing out this f double prime. This chart is not enough. Now we are concave down. On our interval from 0 to 2 because f double prime of x is less than 0. Now remember, our point of inflections happen where we change signs. So 0 and at 2, plugging those back into the original, because the point of inflections are on the original graph. When I plug in 0, I get 0 times 4, which is 0. When I plug in 2, I have 6 times the cube root of 2 are our point of inflections. Okay, second derivative test. This is an important test, and it helps us find maximums and minimums, and it's going to help us in some applications we get to later on. So if your first derivative equals 0 and your second derivative is less than 0, you have a local maximum. How I remember that is I look at a parabola. A parabola that's concave down. The vertex is an absolute maximum at that point because here the first derivative equals 0 and your slopes of your tangent lines are decreasing. For all of those, I go from positives to negatives. That's decreasing. Now we have first derivative equals 0, but I'm concave up. That means we have a local minimum. And again, in this case, I also think of a parabola. That vertex, when our parabola is facing up, that's concave up. I often think of concave up as holding water. Concave down is not holding water. And first derivative equals 0. Second derivatives for all of these are increasing. I'm going from negatives to positives. Okay, using our second derivative test to find local extrema. So first we find our first derivative. And I set that first derivative equal to 0. So that gets me my x values of plus or minus root 2. Now I find my second derivative. And my second derivative, in this case, is equal to 6x. So now you find f double prime of both of those critical values. F double prime of square root of 2 is equal to, I don't know why I'm having trouble just plugging in a value, which is greater than 0. So I'm concave up by the second derivative test we have a max. I'm sorry, there's a min because I'm concave up. There's a min of, I'm going to find the value in a minute, at x equals root 2. Now when I plug root 2 into my original function, I get negative 4 root 2 plus 5. Now, honestly, you don't even have to find the value. As long as you tell me when you plug in this value, I'm getting less than 0, we can now say by the second derivative test, there is so my second derivative, I'm concave down, which means I'm down at my maximum, so there is a max of, I'm going to fill in the y value here in a minute, at x equals negative root 2. When I plug in that negative root 2 value, we get 4 root 2 plus 5. That is it for today. Please make sure the lesson summary below this is submitted on time.